Hey everybody, I hope you're doing well, and thank you to everyone who's joined us for the second Neural Audio Plugin Competition live stream. We are here with the team from Qosmo and also with Gabriele Bunkheila from MathWorks. And today we're really excited because so many people have been asking us during the course of this competition, how can I get started building a neural audio plugin? And in this workshop, we're going to show you how using two different tools. One of those is called Neutone, which is developed by the Qosmo team. And the other way is using MathWorks Matlab that Gabriele is going to show you afterwards. Before we get started, just wanted to talk a little bit about the competition itself and what I could do. And what I can do is, I'm just going to go to my notes here and share my screen. So if you joined us for our presentation last week, this is the same presentation, but I'm just going to go through and zip through this really quickly. So many people have asked, what is a neural audio plugin? Neural audio plugin is a audio effect plugin that uses a neural network to process or generate audio signals. And so what we would like for people to do is to team up and create their own neural audio plugin. And we have a submission process along with cash prizes. So of course, the first prize is courtesy of one of our sponsors, TikTok, Juice, and Cycling 74, with a $2,000 cash prize in either your choice of a Juice, Indie, or Max MSP and Rainbow license, and also tickets to NAMM and an opportunity to present courtesy of GPU Audio. Then we have the second prize, which is courtesy of us here at the Audio Programmer, Qosmo, Juice, and Cycling 74, which is for $1,000 prize, and also your choice of Juice and Juice or Max / Rainbow licenses. And then the third prize is courtesy of GPU Audio for a cash prize of $500. Some people are asking, well, what is the judging criteria? And here is the criteria for this competition. We're judging on novelty, versatility, usefulness, performance, and character. And people ask, how do I enter? So the way that you enter is you go to the audioprogrammer.com/neural-audio, and the link is also down in the video description. And here we have all of the information about the competition. So you can see our sponsors here, and big shout out to them. A description of the competition itself, who it's for, how you can enter, the terms and conditions, and all of the details. Another question that people have asked is, how do they communicate with other people that are looking at entering the competition? How do they ask questions? Well, we have the Audio Programmer Discord, which is now just broken over 9,000 members, and we have a special room here called Neural Audio that we have made just for this competition. As we can see, there are some people that are asking questions here now, and it's been really lively. So there are people in here that have been looking to team up with other people. So some people may have skills in a framework like Juice or Matlab, and looking to team up with somebody who has experience with machine learning or with neural networks. And this is a great place where you can actually join in the discussion and ask questions and offer to help others. The way that you can join that is also on that web page that I showed you earlier, and I also have the link in the video description below. And that's it for the housekeeping. And with that, what I'm going to do is I'm going to go ahead and pass it over to Team Qosmo, and they're going to show you how to build a neural audio plugin using Newtone. Over to you, Team Qosmo.
Yeah, thanks very much, Josh, for that introduction and for going over the NAP competition as well. Hopefully, a lot of people will find that information useful and will get excited about contributing to the NAP competition. And hopefully, through these workshops as well, like we can really educate people and give them the tools and the know-how to build some really sick models during this competition and for them to submit to the competition. So anyway, let's get started with the workshop for today. So I'm just going to share my screen. Should be good to go. So let's see now. Okay, I think we're good. Slideshow. Cool. So yeah, welcome everyone to the second live stream. And this week we're doing the workshop. So yeah, ourselves from Qosmo giving this workshop on Newtone, and then we've got Gabriele giving the workshop on the Matlab toolkit stuff as well. So very exciting week and a lot to share with you today. So this is this workshop on Newtone, which is a real-time AI audio plugin and SDK. If you don't know who we are, this is the lineup of our speakers for the Newtone workshop today. So there's myself, Andrew Fyfe, who's an AI application engineer at Qosmo, and I'm also a PhD researcher at the University of Glasgow. We've got Chris Mitcheltree, who's also AI research engineer at Qosmo and PhD researcher at Queen Mary University of London, and Naotake Masuda, who's a AI research engineer at Qosmo and PhD researcher at the University of Tokyo. So yeah, you can obviously feel free to ask us more about our PhD research, but it's all in the realm of sort of AI audio and neuro audio. So yeah, we're all equally as passionate about these sort of technologies. So today's agenda, we've got quite a lot in store for you. It will initially be with myself giving you an overview of the Newtone platform, the different components that make up Newtone. I'll then dive into the plugin, give you an overview of the Newtone plugin, what models are available currently, the features that are available through the plugin, and then I will give you a live demonstration, and hopefully it goes well. You know how live demos go, but looking forward to having a play and you know show you guys all the crazy and creative stuff you can get up to using the Newtone plugin. And then I'll hand it over to Chris, who's going to talk to you about the Newtone SDK, walk you through the workflow for building a model and all the features and information that is there to do with the SDK, and so you're well equipped to navigating the SDK and building models for Newtone. Then I'll pass it over to Naotake, who's going to give you a proper in-depth sort of overview of the different neuro audio models that we currently support, and also a sort of end-to-end model wrapping process, so you can see with a simple example how you can build a model, wrap it for Newtone, and import it and use it as part of the plugin. And then we'll wrap up with some community contributions so far, like what you guys have done so far with Newtone, and discuss some of the things we'd like to see going forward, and you know the features we'd like to bring to Newtone, the kinds of models we'd love to see you guys submit, and yeah, we'll be open for questions at that point. So let's get started. So what is Newtone? For those that don't know, Newtone is a platform that's really aiming to bridge the gap between the AI audio research community and artists and musicians and producers, like the creatives that want to actually harness and use these technologies as part of their creative workflows. So this is it here. We've got the audio creators, the musicians who are jamming out like with the tech, and then we have the AI researchers who are innovating in this space, and a lot of the time these are quite disconnected areas, and a lot of the creators who are want to use the latest technologies to explore and express themselves in new ways can't access them, or they're not available. And same for researchers. Researchers may want to actually try and get their technologies into the hands of creatives quicker, and also to iterate on their model building process. They may want to use a tool that can really streamline the workflow for iterating and improving their models. So this platform addresses those sort of key areas. We also have a community which brings together these, the artists and the musicians with the researchers and devs into the one space, so that we can communicate and, strive to build better and better models and more useful and impactful tools for creatives. So yeah, make sure to check out the Newtone.space website, where we have all the resources, the download links for the plugin. We have some blogs there, and just all the information regarding Newtone is on that website. There's also the link to join our Discord as well, where all the conversation's happening. So be sure to check that out as well. And the main reason we decided to build a platform like Newtone is because in the past couple of years, this space has been so fast evolving. Like we've seen, really heavy neural audio models like that had been innovated initially that were running that weren't fast enough to run in real time, so or maybe less appealing to some creatives to use. But we're into this territory now where we've got algorithms and neural network algorithms that are coming out that are running in real time, and that opens up a whole new dimension of expressiveness for musicians, and being able to perform these models in a live context as well. So these are just two examples of some of the innovations that have came out in the last couple of years. We've got DDSP, which is both these models, are this a timbre transfer kind of model. So this is the concept, or this idea of translating an input sound to some sort of output sound. So you can imagine maybe like a drum sound being translated to speech, or like piano to violin. It kind of works in that sort of way. So we've got DDSP, which works on monophonic signals, and we have Rave as well, which is also another timbre transfer effect, which can work on a multitude of different kinds of signals as well, and runs at 48 kilohertz sample rate. And it's just a really fast evolving field of research. So there's more and more algorithms coming out all the time. To give you an example of this timbre transfer effect that I was mentioning earlier, this is I guess an example for you to listen to. Hopefully you can hear this. So this is using DDSP. We've got a violin here and coming in at the input, and it's been translated to like a shakuhachi flute sound. So this sounds like this. And that's been translated to this sound. And then the same for Rave. We've got, in this example, violin being translated to speech, so the violin. And then translated to speech. So yeah, a lot of fun there. You can kind of get an idea or intuition on how these timbre transfer effects work. So currently, one of the main reasons we decided to build something like Newtone is because for those who were interested in applying neural audio effects to their creative workflow, or for even wanted to get these neural audio effects to run as part of the DAW, it was a really cumbersome and time-consuming process. Usually, initially start with building a model in, say, a framework, like a deep learning framework like PyTorch. You need to train that model, which again is potentially a costly procedure. Take a long time to train a model to a level of fidelity that might be useful. It requires some GPU acceleration, and yeah, sometimes it's costs and time that you don't have. Again, like we haven't like catered for a solution that like handles this exactly, but like it is part of the process which you need to be involved in normally. And then once you've trained a model, you would typically run inference on that model to get a result. So say you've got some input audio and you want to like run it through your neural network and get some output. You would need to run that through the command line using some, an inference script that would run inference on your model. And then by that point, if you survive, you can actually, use that WAV file and drop it into your DAW and actually start being creative with it. But as you can see, it's quite a cumbersome process, not very streamlined. There's lots of obstacles and friction. And yeah, we tried to address a lot of this with Newtone, tried to streamline this whole process for researchers and those interested in deploying neural audio models in the DAW environment. So, and I should say on top of that, developing audio plugins requires that expertise and knowledge as well, on top of all the ML stuff. So again, it's like quite a lot of different skills that are required to build a plugin that would use neural audio technologies. So again, Newtone is a solution to those that maybe have great ideas and skills in the ML world and want to just build a model and get it in the DAW as quick as possible. So here is our release video for Newtone. And I always love showing this off, these sort of workshops and presentations, because it really showcases how musicians and artists can find value using Newtone in their creative process. So this is Big Yuki, who we partnered with, as part of his creative process, using Newtone to compose new music and also for live performance. So I'll play this first, and you'll get a better idea, understanding on how Newtone can be integrated into the creative workflow of musicians.
この本には2小節の音楽の断片が多数収録されています。サイコロを2個振って出た値によってこれらの断片を並べていき、一つのまとまったが
What's up? Big Yuki here. And man, Newtone is the happy accident. It gives me all kind of new ideas. I can't wait to write some crazy using it. Stay tuned.
Oh shit!
Yeah, so as you can see, Big Yuki there having a lot of fun. I always love how, that sort of surprise he gets from like working with the models as part of his creative processes. Because this is such a new space, new territory, there's so much kind of exploration that goes on with working with these technologies, which is always great to see. So moving on to the plugin, I'll give you an overview of this, all the key components of the Newtone plugin, and then we'll dive deeper with a demonstration. So I should start off saying like the Newtone plugin is available as a VST3 audio unit and standalone app. It's available for macOS, Intel, and ARM native, as well as now Windows 10 and 11, which we released quite recently. This is what you'll be greeted with when you open the Newtone plugin or app. You'll see here there's the model browser, where we list our catalog of available pre-trained models that you can just equip and use. And then to actually control and interact with the models, we have the control panel, which it swaps to the control panel once you have loaded a model. We have a number of different architectures and models in our catalog so far. So like mentioned earlier, we have DDSP models, rave models. We even have temporal convolutional network models as well, and plus a couple others. And these are all available and ready to use straight out of the box. If you're a musician, producer, artist that just wants to start getting creative, they're all there and you can download them from within the plugin and then equip them, start using them straight away. Now to give you more of a overview of the different menus and components of the Newtone plugin. Like mentioned before, we have the model browser, where you have all the catalog of models, as well as you can filter and search for the models that you're particularly looking for. There's the ability to load your own model that you've trained locally. And also there's the About menu, which gives you more information, plus links to our resources as well. The filter option has, as well as searching, you can also, there's more advanced features that allows you to filter for certain tags, the author, the date published, and it sorts alphabetically as well. So you can use this feature to kind of explore what models are available. There's the About menu, like I mentioned as well, which shows the version ID, as well as gives links to our documentation, link to our Discord community and social medias. And then once you equip a model, you've downloaded your first model, you've equipped it, it will take you to the control panel page. And this shows an interface, which is a range of custom parameters, global parameters, and presets as well. So just to give you more insight into what these are, we've got the global parameters, which are the larger rotary knobs there. They are controlling the audio inputs and outputs, certain parameters like the mix, so the wet and dry mix, the level of your input and output audio, and input gain and output gain, so the volume of your input and output audio as well. The custom parameters A, B, C, and D are sort of generalized with those names because those parameters actually hook into the specific model that you're using. So for each model that you equip, they all have different parameters that are specific to that model. So when you build your own model as well, you can export and assign the parameters that you want, and these will automatically be hooked up to the custom parameters here. To allow you to control your model. So yeah, I think we're at the Newtone plugin demo now. So I will come out of this first of all and share my Ableton Live session. So in this example, we've got a range of different sounds here. I've been playing about with some different variations. We've got a sort of pad-like sound, which I'll show you here if I bring down the wet and increase the dry here. So this is like our raw input sound. And then we've got equipped in this particular example, we've got this rave choir model. So just to kind of show you how I got there. When I launch the plugin, this menu comes up, and I've got a large selection of models that I've already downloaded. But yeah, essentially you just equip that model here. So you go like use. So this one is the rave choir model. Takes you to this page, the control panel page, and then you can start interfacing with it. So that was the audio input that I just showed you. Let's see now what the affected sound sounds like when converted to the choir sound. So that's the sort of effect you get when running that pad-like sound through the choir model. Now, so we have a bunch of different parameters here that we've exported. They're quite technical, apart from maybe like chaos, which is quite an interesting choice for this parameter. I guess it's adding like random noise to the latent vectors. So let's play around with these parameters and see like what interesting textures and sounds we can get out of this. So yeah, endless fun there. And that was just like with a constant drone light pad, you know, and there's so much variation that you can get out of that. Let's move to another example, maybe something more percussive this time. So I'll mute that channel. Let's have a look at
As
this
as you're
one.
doing that, as you're doing that,
Yeah.
Andrew, we got a question in the chat
Oh
uh,
yeah, go for it.
from Gary who says, "What are the limitations and constraints on the input training signal? I.e., suppose I use my singing through a delay and a flanger as the input. Does that make any difference?"
Well, actually, that's I guess part of the exploration process of working with these sort of models. So, like, we've actually found that doing some processing of your audio in different ways. So, like doing a delay, maybe putting it through a chorus like effect, maybe adding compression. It all affects how that sound is translated in the output. So, you know, some models are actually trained on are trained on certain kinds of sounds that have particular qualities in like pitch and frequency information. So sometimes you actually get better results if you like do some pre-processing, like shifting the information into like a range that is more responsive with that particular model. Again, like if you want to play around with effects as well, you can, it all affects the generation of these neural audio models, like how they generate. So it's all part of that exploration creative process, working, you know, doing these pre-processing techniques to try and get more out of the models that you're using. So yeah, that's to give you an idea of like, we welcome that sort of thing. It's going to enhance the whole experience, I think, as a creative and artist working with this sort of tool.
Great.
Okay. So yeah, let's have a look at this example. I think I've got it equipped. Let's see. Yeah. So okay, so this one I have some kind of percussive sounds, I think. Oh, that's not what I want to do. There we go. So there's like grooving out on that. We have on the output a model which is trained on human voice, English sort of voice, I suppose, English speaking voice. So this percussive sound has been translated to sort of voice sound. So let's hear what that sounds like. So yeah, quite a strange kind of output, but let's play around with some of the parameters and see what other types of sounds that we can get out of this. So there was subtle variation there. Again, it depends on what model you're using, but like it's always interesting to hear like the slight changes in how the model is generating and responding to the input. Again, bringing down the input audio, you're getting like all these like whispers and yeah, it's quite weird actually. Quite intense. Anyway, that was more percussive sounds. Let's move to another example quickly. This one was yeah, like a monophonic signal. I think it was let's hear what it was again. Oh, that's not the one. That is not the one we're looking for. We're looking for this one. Right, so it's like a bass lead. And on we've got the DDSP saxophone equipped for this example. So let's see how that sounds. So in this example, I can also remove the harmonics of this type of signal and only hear the sort of breathiness that's left, the sort of more, I guess it's also termed like stochastic sort of component of this sound. So let's hear what that sounds like. We can remove that. So yeah, that was a few examples of some, I guess, ways you could get creative with these sort of models. So we had 2 rave models there, different sort of use cases, percussive sounds, drone-like sounds, and we also had a monophonic sort of bass lead being converted to sort of a saxophone-like sound using DDSP. So I think that is the end of this particular demo. So I'll just show you actually quickly some of the options here. So like loading your own model. So Naotake is going to show you more about this later on when he takes you through building a model, but this is how you would import that into the plugin. We've got the filtering here. So we can actually just select tags for certain models. So there's also that, and then the about window where, like I said, mentioned earlier, you have links to our documentation, our Discord community, and social medias, as well as like the version number down there as well. And yeah, I think that is everything. So I'm going to come out of this demo now and get back to the slides. I'll probably be passing it over now to Chris, who's going to take you through the SDK and give you more insight into using the SDK and how to navigate the SDK and what features we have as part of the SDK. So I'll stop sharing now and pass it on to Chris.
Great. Thank you, Andrew. That was fantastic. All right. All right, cool. How does that look? All right, so I'm going to talk about the SDK a little bit. So the SDK is basically meant to make your life easy. Some of you may just be beginning to learn how to develop plugins, and some of you might be experts, but I'm sure this will be kind of a non-traditional approach to making a plugin, and I'm going to go over a little bit how Neutone does what it does. So as Andrew just pointed out, in the plugin you have at the top this load your own button, which is kind of where the SDK shines because it lets you write code in Python, not C++, to build a model. And this is because most neural networks and neural models are built using Python. The tools are very developed, and it's much easier to write your own neural network or audio processing system in Python than in C++. So the idea of Neutone is that it enables the user to easily write their model in the SDK with a bunch of help from SDK that takes care of a bunch of things that you might not want to deal with. And I'll go over some of those in a second. But you can focus purely on building something cool that sounds good. And then also very importantly is being able to test your model quickly and iterating, because that's a really big part of building a new audio effect, is being able to hear what is going on. And that's currently another limitation with neural models, is typically you have to be quite, literate with Python and how to run, scripts in the terminal to process some audio in a directory and then output the audio, save it somewhere, listen to what the output is, and then do that over and over again, which can be quite slow and probably is not the ideal way to prototype something quickly. But with Neutone, you can write a model, change a few things, export it in 10 to 20 seconds, load it into the plugin, and then hear immediately what's going on and change, the parameters on the fly and get very real feedback. So I'm going to talk a little bit about the SDK and what it offers you. So the SDK is available on GitHub under Newtone_SDK, and it comes with a README that has documentation on what it offers and some links on how to get started, which Naotake will go over a bit more. But basically, there's two things that you want to do. The first is you want to download the plugin from the Qosmo website and have that running in your favorite DAW or wherever you like to produce music, or just use your plugins. Then secondly, you want to download the SDK through pip is the easiest way. So if you're developing in Python, you can install the SDK with pip, or you can just download this Git file if you're more familiar with that. If you're not familiar with Python at all, then there's also Colab notebooks that we provide, which we'll also be going over in a second, so no worries there. And then here I'm going to go over the development workflow. So how does somebody who wants to build their own model, how do they do that using Neutone? So as I said, you go to the website, you find SDK, you might open one of the Colab notebooks that walks you through how to train a model, or you might load it up in your own local environment. Then you also go and download the plugin, which you can then load into your favorite DAW. For me, it's Ableton, so that's shown here. And then in the SDK, you would write your model in Python. It could be something very simple or something very complex. And then you would export the model using the SDK, which then will output a .nm file, so model.nm, which you can then load locally in the plugin. So you just on the load local model, and you can immediately start to use that model. And one thing that's nice is the model is automatically converted to C++, which then is compatible with the VST and the audio unit and whatnot. So this is kind of a loop, because you'll be spending time writing code in Python and only focusing on your on how you want your model to sound. So you don't have to worry about some of the other detail of building a plugin. And then you just load it into Neutone. It should work out of the box. You can try it out in different settings, different audio, different parameter settings. And then you can make changes and keep iterating until you're happy. And then once you're happy, you would submit it as a GitHub issue. We have a template. It's quite simple. You just go to the GitHub again and submit an issue, and you would upload the model that you trained, and then we would take a look at the code and just make sure it runs and works properly. And then we would upload it to Amazon 3, which hosts the models. And then from there, whenever anybody around the world loads up the plugin, it'll be available in the model browser. So you'll be able to use that model out of the box, and everybody else will be able to use it as well. So it's a really cool way to immediately share what you're using with all the other creative people that have the Neutone plugin. So that's kind of the workflow and life cycle of model development. So the thing that some of you might know is building a universal VST, or building a VST in general, is quite hard. I mean, that's why we have amazing communities like the Audio Programmer, because it's quite a steep learning curve. And as some of you might be familiar with, there's a lot of factors that need to be considered. So for one is that, you have a DAW, which has a bunch of settings that can change at any moment. And this includes the sampling rate of your DAW. So typical ones are like 44, 100, or 48 kilohertz. You have a buffer size of how many samples there are, and that also dictates delay. And you have to also, like your plugins have to communicate to the DAW how much delay they introduce so that they can synchronize the tracks with all the other tracks. Otherwise, you get kind of a mess when you're playing back multiple tracks. And then on top of all of that, you need to be wary of your CPU usage, since you can't be, doing too many calculations that the audio doesn't come out in time. And taking care of all four of these things, also the parameters, for example, of a model need to be customizable. This is already hard enough for a single plugin, like a reverb, let's say, or a filter, right, which has a singular purpose. But with Neutone, we're trying to make any model possible. So we want to enable all models while still being able to handle these specific conditions. And this goes against kind of the paradigm of VSTs, which are typically very specific and have a very specific purpose that they were built for. And then finally, on top of all of this, we have neural networks, which can be flexible, but in general, they are trained on a data set and they have an architecture that is defined. So this is an example of a temporal convolutional neural network, which is a common way of processing audio. And the issue with this is that TCNs or neural networks in general, they might be trained on a data set that's a specific sample rate, and they might require a certain number of samples. So your neural network might have very different requirements than your DAW. So you need to translate between the two seamlessly. And this is like not trivial at all. And the rabbit hole that everybody goes down when they start to write a universal VST for neural audio effects. So the SDK kind of handles all of this for you and is trying to make your life as simple as possible, that all you need to focus on is building a model, but you don't need to focus about all these kind of details that will bog you down. So we kind of had these two worlds that are apart from each other and need to be bridged. So we have the DAW world, where you have sampling rate, a buffer size, stereo or mono tracks, and delay reporting. And this can change at any time for any reason, and every computer might be different and have different capabilities. And then we have a Neutone model, so something like a a neural network, or what Andrew was showing, these timbre transfer models, which have a fixed sampling rate because they're trained on a specific data set with a fixed sampling rate. They also require a fixed amount of samples. So for example, a lot of the timbre transfer models require 2048 samples. And they might have a weird combination of stereo in and stereo out. So the other thing with neural models is that they can have any combination of mono and stereo. You can have a model takes in 2 channels and outputs 1 channel, or what's even cooler is you can have a model that takes in a mono audio track and then encodes it into a latent space and then samples that latent space slightly apart from each other, create a stereo effect. So there's these unique possibilities that neural models enable, but we also need to handle these kind of more kind of weirder scenarios where you have mismatching channels and things like that. And then finally, the model also can introduce delay, which then needs to be returned to the DAW and also needs to be accounted for if the sampling rate is different. So overall, we need to guarantee that the model requirements are maintained and guaranteed while we handle any combination of DAW settings. And this is kind of the thing that we thought might not be that difficult and ended up being a lot of engineering effort. But I think we've reached a point where it's quite nice because we can do a lot of the things that we're seeking to do here. And the way we do this, for a high-level overview, is for sampling rate, we do automatic model sampling rate selection. So models can support multiple different sampling rates or even all sampling rates. And then we do real-time resampling to the correct rate automatically, so that your model is always receiving the correct type of audio. We do a lot of buffer and automatic buffering of samples as they come in to ensure the model always has the correct number of samples, and this is also not easy to do. We do automatic mono stereo conversions. This is a bit easier, but this is also handled for you automatically. And we do automatic delay reporting, which becomes non-trivial with the buffering and the sampling rate. And I'll give an example in a second where it becomes very clear why this is hard. So here's a concrete example. Let's say we have our DAW is set at 44100 kilohertz and as a sampling rate, and then we have a buffer size of 128 samples coming in with a stereo track. This is a pretty typical scenario. So then let's say we have a Newtone model that was trained on 48 kilohertz with a buffer size of 512 or 1024. So the Newtone will automatically select the best buffer size and sampling rate. And in this case, it's quite easy because there's only a few options, but it can sometimes be non-trivial. Then we're going to calculate the resample buffer size. So for going to 44100, we have to resize to 139. And this is now the internal buffer size of Newtone. And then we can calculate the minimum buffering delay, which is from waiting for the buffers to arrive. And this number can be very weird to calculate because it depends on kind of the remainders of the two buffer sizes. And if they're kind of a very weird ratio, for example, 139 is kind of a non-even number, this calculation can become strange. And we support any buffer size. So you can, it doesn't have to be a power of 2, it can be anything. So we have to be able to support all these weird numbers, and we can't really make any assumptions because even if we only say, powers of 2, once you have to resample to another sampling rate, that number can change drastically. So Neutone handles all of this, calculates the correct numbers, and then allocates all the internal buffers and queues to prevent any memory allocation happening when you're doing inference, which is when the audio needs to come out in real time. So then now for a concrete example of what happens to the audio. So you'll receive a buffer from the DAW, and this will be on the C++ side for the VST. And then we move the buffer over to the Newtone SDK. So everything in the gray box with the dashed line is actually happening in Python, which is then compiled to C++ using TorchScript. So this is how we can enable a ton of flexibility with the SDK while still being reasonably performant and running it in an SDK. And all of this is also happening in a background thread. So this helps us be a little bit safer because running a neural network is inherently not necessarily a real-time operation. So we move the buffers over the background thread. And then in this case, we have a Newtone model that takes as input mono and output stereo, which is similar to the example I mentioned earlier. So we will convert the buffer to mono automatically, and then we're going to resample the buffer to the correct sampling rate, which makes it slightly bigger. And then that buffer is going to be put into an input queue of mono audio, which will guarantee that the model will always have enough audio to work with, no matter what the buffer size is of the DAW. And then the model will take buffers of 512 samples, which is what it was designed for, and then process the audio, output it into an output queue, which is now stereo because the model outputs stereo. And then that gets resampled again to the correct buffer size, which is then output to the VST, which then gets sent to the DAW, and that's what you hear at the other end. So all of this is kind of happening thousands of times to generate the audio. So the reason I think using Newtone is really nice is because you don't need to worry about any of this. All of this is taken care of, and it gives you much more freedom to use whatever neural networks you want to use without having to consider these very strict limitations that DAWs kind of impose. And we try to make your life easier by also providing a bunch of features in the SDK. For example, we include cached convolutions, which are very important for real-time audio effects that are streaming. So they're operating on audio as it comes in. So this is included. We provide temporal convolutional networks, which are a very common audio effect and run very fast. We have highly efficient circular audio queues that let you, take care of queuing audio and samples without you having to worry about it. And this also gets all compiled to C++. And for example, we can handle a look-behind buffer. If you need a lot of samples at input, but output a smaller amount of samples, you can do that easily with a look-behind buffer. And finally, we also give you a profiler, which lets you check how fast your model is running and can give you an idea of if it's real time or not. And yeah, so the SDK enables rapid prototyping because it's compatible with most DAWs, like the Newtone, the plugin runs in most DAWs, and it lets you load and export model locally. So you can just run your changes really quickly and then load them into the model, and that's good to go. And one thing that's cool is you can use Ableton or something else to map the parameters of Newtone to a physical MIDI controller. So that means you can explore, latent spaces of models or, something that might be very awkward to change with the mouse with your hands kind of in real time. So you can get a lot of these happy accidents that, only can occur when there's a very creative session where you're not hindered by the interface that you're using. So that's another benefit. And then finally, recently, we also added a spectral wrapper because right now the SDK was built for audio to audio effects. So this means you're operating on the raw waveform, which is kind of the default, I would say, for many audio effects. But there's also audio that deal with spectrograms, like a spectral delay or a spectral filter, or Ableton recently added 2 spectral effects as well. So like spectral reverb is one of them. So we wanted to add the ability to work with spectrograms because some people prefer working with kind of images rather than raw waveforms, and it opens up a new type of audio effect that you can work with. So neural networks that are optimized for spectrograms exist and can be used to create more interesting effects. So the spectral wrapper in the SDK, it takes the incoming waveform and converts it to a spectrogram, which then can be used by your model to manipulate. And then you can give it a modified spectrogram, which then gets converted back to audio automatically. And a really big issue with spectrograms is phase information, because it's hard to recreate the phase on the other end. So we provide the option where you send the phase information over so that you can deal with the magnitude spectrogram, but keep the phase. And this is useful for, effects that are just changing how much of a frequency are in the signal, but not like wants to preserve the phase. So some things you get for free with the spectrogram wrapper is you can have different spectrogram modes. You can work with a strictly positive spectrogram, so you can ensure it's between 0 and some positive number. You can make it logarithmic. A logarithmic magnitude spectrum is really popular. You make it a power spectrogram. You can save the phase information. There's different modes for that. And most importantly, it supports crossfading correctly, which allows you to make very smooth effects, because the edges of the spectrograms can be kind of slightly different, which can create an artifact when you put them back together. So this ensures that you have kind of a nice, clean audio coming out once you've converted back. And we've implemented this that, once again, it minimizes dynamic memory allocation so that it runs as fast as possible on like in the C++ world. And there's other common errors that can trip you up with like when working with spectrograms. So that's why we encourage using it as well. So I'm just going to give a quick tour of the SDK, and then we'll move on. So this is the, I'm going to make it a bit smaller. Okay. So when you use the SDK on GitHub, you'll see we have a couple different folders. So the main thing you want to look at are probably the examples folder, and actually the README is probably one of the best files. So the README is probably the first thing you want to look at. It includes a lot of information about what's going on and how to use it. And for those of you who work with Python, it should be quite familiar. And for those of you who aren't, it should still be a good starting point, because like I said, you can also use these Colab notebooks that do a lot for you and do it step by step. But once you're familiar with that, you can check out the clipper, which is kind of our very first starting model. A clipper is a very simple effect. It just clips the audio and distorts it. And it's not even a neural effect, but it's a useful place to start because it's probably the simplest thing you can implement. So for the clipper, you would have a model which does the clipping action here. And then the important part is the SDK. It takes about 10 minutes to wrap a model. So you would basically import Neutone in Python, and then create this waveform to waveform base, which is the wrapper that we wrote to wrap your model. And then basically you just have to implement these different methods. So the name of the model is a clipper, the authors, the description, maybe some technical links, and the version number if it's experimental. And then here you can define up to 4 parameters that do different things, like minimum, maximum, and gain, which is typical for a clipper. And here you would want to say whether the input is mono or stereo. So this would be false because it's stereo. And then here you would also give the sample rate. So a clipper works on all sample rates, so you can just leave it empty. And it works on all buffer sizes. It can also be empty. But for example, for other models, you might want to guarantee 44, 100, and here you might want 512 samples or something like that. And then in the forward pass, you would simply define that you get your parameters out of, they're passed in here in the dictionary. And then you just do the forward function of the model and return X. So this is a very simple example.
Associa.
And then the other example I'd like to give is the spectral filter. So this is what I was just talking about, where we have a spectrogram that we want to work with. So for this model, it's just implementing a pretty simple filter where it gets a spectrogram and then attenuates certain bins in the spectrogram using a kind of filter shape. The details of this aren't so important. You can check out the comments if you want to see what's being done here and just play with it. But once again, for the spectral filter wrapper, you would define your model, and then you would say how many frames of the spectrogram your model expects. So in this case, we have 16 frames, and then some spectrogram parameters like 2048, bins, and a hop length of 512. And this is the crossfade, which is very important because it ensures that the output audio doesn't have any artifacts. And then it's very simple. We initialize this real-time STFT class here, and then we simply fill out the same methods as before. And then in the forward function, which is the one part you have to fill out, you get your parameters. So in this case, it's a notch filter. So we have a center frequency, width, and amount. We convert to a spectrogram. So here we do stft.audio to spec. And then here we can pass the spectrum into your model, which then converts the spectrogram. And then here we convert it back to audio. And that's it. So it's 4 lines of code. And this model is up here. It's taking the spectrogram, it checks where the bin is, and then it makes it smaller by multiplying it by some factor. So this is how the filter is working. And then lastly, I just want to, if you're interested in all the other options, you can go into the Newtone SDK, which has this waveform to waveform file. And in this file, you can see all the different methods that you have access to. For example, you can get look behind samples. So here you can override this method to provide 512 samples of look behind. So this is very useful if you're dealing with that. Or, if you're just interested in what's happening under the hood, you can see what's going on here. And lastly, we have a profiler. This is profiling the Clipper model. So just an example. You can just run this and it will profile the model and then output, how fast it is and what's going on. And you could replace this with your model quite easily up here. So this can give you an idea of whether your model will run in real time or not. But the easiest way is also to just try it in your DAW and see how it sounds. Usually our ears are a very good indicator if things are going well. But yeah, I think that's everything. I'm going to pass it on to Naotake, who's going to give some examples of training your own model. And I hope, just to wrap up, the SDK basically is trying to make your life as simple as possible. And it gives you the ability to write code in Python that then becomes a VST, which is very, very nice if you don't want to write C++ code, or if you want to do these kind of complicated neural models that might be very difficult in a C++ world, while also handling all the DAW requirements and all the things that are non-trivial in the background. So yeah, I'm going to pass it on to Naotake, and you can take it away.
Right, let me just share my screen now. Okay. All right. Okay. So I'll be discussing how to create models and so how to create models using Colab notebooks and etc. And I'll also be giving a brief overview of neural audio effects in general. It's there's no math involved today, so don't worry about it. So basically real-time neural audio effects is a pretty upcoming field, and I guess it can be split into 2 main directions. The first is effects emulation. So basically you train a neural network to replace a conventional effect module. So this network is trained to predict the wet signal from the dry signal, and in that sense we call that a supervised sort of problem. yeah, it's basically the same as like black box modeling, which is like also an like existing technique, I guess. But yeah, but modeling the effect using a neural network sometimes allows us to like, modify it, sort of bend it in like different ways to get like cool sounds. And that's also like a big advantage of this approach, I guess. An example is like time convolutional network. Yeah, so time convolutional network, I'm going to like give a brief overview of the Colab notebook, and you can train that. I mean, we're going to show how to train that like, in this stream right now, like after like explaining a bit. And then like the second type of model is time transfer model, and I guess you've seen like the examples by Andrew. So time transfer converts the input audio into that of like another instrument, or just, I don't know, generic sound like timbre. And this is like a type of an unsupervised problem. So you only need like so to get like a violin sort of timbre transfer model, you just get a bunch of violin sounds and train the autoencoder. And that model would like allow you to like transfer any sound into violin, because the way the autoencoder works is that this autoencoder is trained to like reconstruct the violin sounds. Like the input is the violin and the output is the violin, and it compresses the information and all that. So this intermediate Z variable is like called the latent variable, and that sort of encodes the musical information like performance, like pitch, loudness, etc. And when you feed the network like piano sounds or like any sort of like out of domain sounds, the encoder sort of extracts the musical information and reconstructs that, but the decoder only knows how to like create violin sounds, and that's how we get like a time transfer effect. There's like two main time transfer effects that we currently support for Newtone. The first is RAVE. So the RAVE network is it directly models the raw waveform of the audio. Wait, well, okay, so like the first, I got the first sentence is like the explanation for the DDSP model, sorry. So RAVE doesn't like make any assumptions about it's like the audio it's modeling, it just models the raw waveform. So you can model like, you can model harmonic sounds, and you can also model percussive sounds. It can be all noisy and stuff. And you can model anything. And that's like the advantage of RAVE models. The disadvantage is that like it's more expensive to train compared to the DDSP model. It's like 3 days on an average GPU. And you also need like more training data. At least more than 2 hours is good. The author recommends like 3 hours or something. And it totally depends on like the data, like type and like characteristics, I guess. But it's difficult to say like whether your data is good enough or not. And that's like the difficulty of experimentation, I guess. And the second model is the DDSP. So DDSP model predicts the timbre from pitch and loudness that's extracted from the input audio. And the advantage of that is like it follows the original pitch very well, because it encodes it explicitly models the fundamental frequency, which is pitch, and the loudness. And also it's this like sort of architecture utilizes what we call like a inductive bias in machine learning, but so it utilizes like the characteristics of a musical signal, which is like usually composed of like harmonics and plot noise. And this knowledge is like encoded into the model, so it's pretty efficient. But the big disadvantage is that it's only for monophonic pitch sounds. So like you can't have like a drum loop, or you can't have like two violins playing like separately. So like I guess like for like sort of out of this world type of sounds, you want to use rave, but for like traditional instruments and stuff, DDSP is pretty suited for that. So we have like 3 Colab notebooks that like you can train the model, and then you can wrap the model with Newtone and like export it. So the first one is the TCN, which is like effect emulation, a simple effect emulation model, and the rave time transfer and the DDSP time transfer. And today I'm going to be going over the TCN. So yep. Wait. Okay. Let me just okay, so this is the Colab notebook. Let me just keep. So first we install like the requirements and import stuff. It should be pretty fast. But I mean, like we have to connect to a runtime right now. So let me just, yeah, so let me just explain what goes inside like a TCN model. So this TCN model is like a 1D convolution that operates over like the time. So so this TCN network is composed of TCN blocks, which are this convolution, 1D convolution. You know, convolution, I think you've heard of like, I mean, if you're not familiar with machine learning, you've still heard of like IR reverbs and all that stuff. It's the same operation, but like these. Yep. Okay, seems like it's installed. Yeah, and like we define a TCN model. It's yeah, there's like causal convolution and all that stuff, which I will explain a bit later. And so we first upload like a clean sound, a dry signal. Yeah. Okay. So like this is like a super simple example. So wait, we only need like one sound, like pairs. So this is a dry signal. I'll upload that. Yeah, it takes a bit to like upload. Yes, but then I'll upload the wet signal. I'll just use like a low pass version of that. Okay, so like this is a dry signal. Did I share the audio? Okay. Okay. Yeah, this is just a dry drum loop. And no pass. Yup. Yeah, there's some weird error messages. Like, I don't know. I think like Google doesn't like that I'm using Firefox or something. But yeah, so this is our target signal. We're just trying to emulate like a low pass filter. And yeah, so we'll just do the training from now. Like, Yeah, and it's a pretty simple, it's a pretty small network with like only 4,000 parameters. And it's pretty shallow, and we're only giving it like this pair of data, so it's pretty fast. It says it'll finish in like a minute. That's good. I mean, yeah, like I actually like saved the results, so like we can already hear the results. So yeah, let's just hear the results, okay? So this is the dry signal. And this is the target signal, the low pass. And this is what the network outputted. Wait, this is like, is this the right one? Yeah, I think it's the right one, but yeah, it's okay. So I think I did this one with the reverb. So yeah, let's just wait for the network to finish. Oh yeah, so this is like the loss function values. When the loss function is like decreasing, then it means that it's like trained properly. Yeah, and this is like the actual results. Okay. So like this network can be used to model stuff like like filters and reverb and compressors and all that. I've tried it with like more extreme like effects like bit crushers and like extreme distortion stuff, but it seems to be a bit worse in terms of that sort of stuff. Okay, so this is a target sound low pass. And this is the modeled low pass filter, like the network output. So you can see like that the high end is like not present anymore, and it's pretty much I think it's pretty similar, but like not perfect sort of. So one thing we have to do before we like convert this into a Newtone model is that the convolutions inside this model needs to be compatible for streaming, meaning that, you know, it has to like take into account that it processes buffer by buffer. If we don't do that, then we get like a sort of a pulse train, sort of well, blips at the start of like each buffer. And then we can wrap the model now. Wait, did I share the link for this in the, I don't think we have. Yeah, I mean, I'll just share the link for this in the YouTube. Okay, so we wrapped the model, I think, and now we'll just save this to the Google Drive. The neat thing about Google Colab is that it just mounts your Google Drive like automatically and stuff. So yeah, it's running the export stuff. And yeah, like our time is pretty precious. So like we'll just say that this it's working fine. Yeah, I already like downloaded the thing. So okay, so I'll just show you how to like load this local model. So like you open the model browser and you press this load your own button. And where did I put TCN LPF button. Yeah, this is the model that we created. Did I? Oh wait, I didn't press that right. Sorry. Oh wait, so it's already loaded. Okay. Okay. Right. So I'll just play the dry signal right now. So this is another drum loop that's not trained, like that's not the training data, but like a different drum loop. And then I'll turn this effect on. So yeah, this is the low pass effect with the TCN that we trained. And then like, you notice that we have all these 4 knobs. So the neat thing about this TCN model is that it sort of automatically finds like interesting parameters to tweak. So like this first knob is controls like how much these 3 knobs do affect on the sound. And so second knob, yeah, the second knob is pretty subtle, I guess. Yeah, the third knob is pretty pronounced. Like it seems to be more of a high pass sort of effect. Yeah, it's definitely cutting the low frequency. So what these 3 knobs are doing is that it's modulating the internal like representations inside the network. Well, it's just messing up like what goes inside the neural network, and that creates like a pretty interesting audio effect. Yeah, so that's about it for this collab. Yeah, so like one thing I need to show about the collab notebook is that there's a sidebar here, and like you can open this and like you can see the files. The Google Drive stuff is like under Drive, My Drive or something. So yeah. Okay, so that's about it for the collab notebook. So like the Rave time transfer stuff is like pretty similar, except that it takes a lot longer. Rave is a bit like difficult to train like on Colab because it's so expensive and like Google wants to kick you out like in the middle of it. So yeah, but people seem to manage, like they're pretty persistent, I guess. Right. So we talked about like this existing models, but you are totally encouraged to like create like new models for Newtone, like alternative architectures. But like in order to do that, so the model has to be written in PyTorch and it has to process buffer by buffer. And yeah, Chris said all this like in much more detail, so I don't have to explain that. But and another thing you have to consider for real-time effects is that if the model is fast enough and if the model is like streamable. So one thing about Newtone is that it operates on CPU. We know that GPU is like great for like neural networks, but it's not so obviously. Yeah, I mean, there's like people like GPU Audio that's like the sponsor of this math competition as well. So like, yeah, they're doing great work on like bringing that to like the audio effects. But like most like music production nowadays is mostly on the CPU, and Newtone is also on the CPU. And so models like Wave is pretty complex, but it still managed to be pretty fast on the CPU because it utilizes many techniques like PQMFs and all that. There are like slow models though, like diffusion models that's like making all the rage is pretty slow. I don't think that could like ever be on like a real-time audio effects, like unless a breakthrough. And there are the big transformer models like Audio LM, like it's pretty interesting, but not very like, I don't think it even runs on like normal GPUs. I don't know, it's very big GPUs, I guess. And so the second like requirement is that it's streamable. So this causal convolution is like one thing that really affects the latency of your model. Causal means that it doesn't like depend on future input. So I guess like filters are like sometimes causal and non-causal. Like if it's non-causal, then it relies on like future input to calculate the current output. So it's like it's like this left diagram. You want to get like the output at step like time t, but you need the input at time t plus 1, and that totally affects the latency of your model. So you want the model to be like pretty much causal all the way. And another thing is that streaming convolution or cache convolution. So yeah, I'll just show like a big diagram. So these are buffers, and like this is the first buffer and like the second buffer. So if we apply like non-streaming like standard convolution on these buffers, so usually CNNs have like this sort of convolutions have this sort of zero padding operation. This zero padding is applied to this buffer and also the second buffer as well. So like, but like if these two buffers weren't separated, then there wouldn't be padding between these two buffers. And that creates a sort of discontinuity. Discontinuity, is that spelled right? I don't know, but yeah. So that's like totally like unacceptable for an audio effect. So the streaming convolution like takes care of this by like replacing this padding with the end of this first buffer. So yeah, so calculation wise, it'll be the same as if these buffers weren't split at all. Yeah, so it's a pretty like lesser known like technique, but there is some like technique, some like libraries for this. I mean, obviously Newtone SDK has the TCN, and you should like look at that and use that for your audio effect, I guess. So yeah, that's about it for me. I would love to know if you have like ideas for models. Like you can, for example, like train these models with like really interesting sounds that you have. So like there's the Colab notebooks, and you could use your own GPU or something, or you could use a cloud provider or something. And yeah, and like you could like expand these models to be like better, like, you know, better controls, like TCNs with like, but you actually modeled like knobs of each effects, like the distortion, like gain and all that stuff. And yeah, we'd love you to see like building new architectures for Newtone. That would be cool. Like this new spectral wrapper is like a good opportunity for that as well. Yeah, so I'll hand it over to Andrew again.
Yeah, cheers, Naotake. That was awesome. Just for the final part of this workshop, quickly, just checking the time there. We will show some of the community collaborations and contributions that we've seen so far. So I'm just going to share my screen. Okay, and then I think that's sharing fine. So we here we go. Okay, so yeah, we have a number of examples here just quickly to show. I won't go through all of them, in fact, just because of the time, but to kind of give you some of the community that have been like interacting with Neutone and using it as part of their creative processes. We have Big Yuki again. Here he is jamming out on the piano. Let's see if this loads. So in this example, he's using piano through Neutone into like a speech model. You hear that being translated. This is an amen break drum model. Yeah, just mayhem going on there, but that sounds so awesome. So, and then this is Naotake from Qosmo jamming out, creating some sort of percussive beats with a speech model as well. I think this is always a fun example. So yeah, just grooving out there. If you want like any of these links to check out the full videos, just let us know. We can post them in the chat. Anyway, I hope that gives you an idea. We've also had some people from the research community use Neutone as part of their research. So we had Caleb Koch from Belmont University use Neutone as part of his experiments, trying to model amplifiers and like amplifier distortion and guitar effects. So he sort of built these models and then like tried them, ran them in Neutone to hear how they sounded. And I think, yeah, made some great progress with amp modeling through that. And this was his poster that he showed off at the end of his project with his results. So it was great to see that. Yeah, so the last, just to conclude on our workshop today, we're really wanting to see more people get involved. We want to see more models be contributed and submitted to Neutone. There's a lot of great architectures and research coming out constantly. It's such a fast evolving space. So, you know, there's, you know, we want to ask also like what sort of models would you like to see, and you know, as models that we want to explore ourselves. You know, there's real-time diffusion being done on like a sort of GPU type inference, which has came out and has been quite interesting. So like a sort of text to audio effect. You know, we've also got like other VAE models like Musica, which generates music in real time. So rather than like translating like a sound to another sound, it's actually generating music, say electronic music or something in real time. We have new versions of Rave coming that have came out recently. We're also interested, and we've heard some people mention that they're interested in running Neutone on embedded hardware, like on the Bella, for example. So we'd love to explore that sort of avenue as well. A bit like Caleb's research, the analog modeling, you know, being able to host and perform tube amplifier emulations like through Neutone as well. Something we want to add more of these models to the Neutone catalog. And then again, veering away from the audio, we're also interested in doing symbolic music generation, so like MIDI generation models as well. And then transformer models, like we may not be able to run those at the moment on CPU, but we'd love to start implementing new mechanisms to actually accelerate some of the heavier weight models on GPU as well. So yeah, so that's kind of where you guys come in, and we hope as many of you as possible like contribute to the Neutone community. We'd love to collaborate with many of you. Like if people have got ideas of features, great features that they want to bring to Neutone, we'd love to work with you, and please reach out. You know, let us know what features you'd like to see. We're constantly working on the platform and on the VST functionality. We'd like to bring MIDI to audio models in as well, and you know, that like that I mentioned earlier, offline rendering for heavier weight neural audio models. And yeah, UI UX, I think that's super important to think about when it comes to these new technologies. Like what interesting and exciting ways can we interact with neural audio models, especially for like live performance and composition. So ideas on how to do some new interactions with these models is also welcome. Your suggestions are welcome there. So and yeah, and extending our SDK as well, adding, it's open source, you could fork it, you can add features to it, and really make it your own. And these are all the people that have been involved in this sort of in Neutone to date, like getting to where it is. Our team at Qosmo, and obviously the guys at Arcam for allowing us to use the Rave algorithms as models and host these models as part of Neutone. So yeah, that's our credits. And yeah, thank you everyone for listening and following along. We'll share all our resources with you in the YouTube and in our Discord as well. So make sure to check out our Discord, because there'll be lots of resources there. We also have the Neuro Audio plugin competition channel in the Audio Programmer Discord. So be sure to go there too for more resources and information. And these are just some of our links as well, just to keep them at the forefront of your mind and to check them out. But yeah, thank you very much for watching. I think we're good to maybe take some questions, and then we can move on to the next presentation.
Yes, thank you very much, Andrew. And what we'll do is we will wait for a few more questions. There is a question here from Christopher, who asks, I know this is a shot in the dark, but will there ever be a TensorFlow SDK for Neutone?
So TensorFlow, we've been so at the moment we're only using the PyTorch framework for TensorFlow, as it kind of is compatible with how we've designed the plugin. Also, PyTorch, the way the framework's built, makes it quite nice for this sort of wrapping and exporting mechanism for the Neutone plugin. But we have been interested in exploring other options that allow us to bring in users of other frameworks to Neutone. So one solution to that is maybe using a framework like Onyx, which allows you to exchange and swap between different major frameworks. So Ollie Larkin, who was on last week, was showing an example of using the Onyx runtime. So the great advantage of Onyx is that you can go from a PyTorch model to Onyx, or TensorFlow model to Onyx, and then use their Onyx runtime to actually perform the model that you've converted. So there is that potential avenue, but I think for the time being we'll be concentrating on the PyTorch version, but we are like thinking about ways in which we can extend to other frameworks as well. But yeah.
Great. Yeah.
Oh, sorry. I just wanted to say, I saw in the chat a question about sustainability that I think I'd like to talk about a little bit. So in machine learning, there's this big problem of we want to build models that run on electricity that use up a lot of energy. And I think the question was asking, first off, how do we balance training these models versus, causing more CO2 emissions? I think there's kind of three ways to answer this. So the first is there's like a really big push in machine learning, which is typically, done by tech companies that happen to be more focused about the environment, I think, than some other companies to be more green. So I know Google Colab is trying to be like fully green with their data centers by 2030. But regardless, of course, there is that. And then the question was, aren't you wasting energy by training, trivial effects on a GPU? But I think the effects that we're showing here are more simple examples on how to get started. And you saw how fast they train with Naotake's code. So it's equivalent to kind of running your microwave for a minute. So I think in the grand scheme of things, compared to like large language models, these audio effects are orders of magnitude faster to train in some cases. But then I guess the last point I think that's good to notice is another way to think about it, even though we want to reduce energy use as much as possible, is as more people get into audio production, which is becoming more and more popular with like the computer, there's also this demand for audio effects, right? And I think some people might go out and buy hardware, which is very, really nice to use, but also has its own huge problems with electronic waste and the use of energy to create hardware. So there's another argument to be made by giving people more effects that are virtual. You could be saving energy on that side or preventing some of this e-waste that could happen from guitar pedals being bought as more people get access to the technology. But I think there's just multiple ways of looking at it, and there's not really the right answer at this point in time. But I think there's hope for the future as well for this.
Fantastic. Steak Proof says, I appreciate you taking the time to answer a difficult question. So thank you, Chris. And thank you to Andrew and Naotake for staying up. I know it's quite late for Naotake in Japan. It's probably about 3 o'clock in the morning over there, or possibly later. So thank you very much for your contribution. And with that, looks like we're done with questions. Thank you very much, Team Qosmo. There is one more question here from Gary Worsham. How big of a pitch range is required for the training signal?
I guess it might be about the DSP model, I guess. It depends, I guess. So like if the model is trained on like a certain pitch range, then it's going to respond to that certain pitch range. So
right.
So if your model is like a bass model, I guess you don't really need a really high-pitched bass sounds, I guess. Like it's just a natural, like, I guess, pitch range, I guess. But that's my answer, I guess.
Yeah, sounds good. Great. Looks like that's it for questions. Thank you again, Team Qosmo. And with that, I will go ahead and move along to our next talk from Gabriele Bunkheila from MathWorks. So today, Gabriele is going to talk about how to build a neural audio plugin using Matlab. So over to you, Gabriele.
Let's see, am I sufficiently unmuted?
You're unmuted.
Cool.
By the way, you can go ahead and for people in the chat, if you continue to have questions regarding Newtone, please continue to ask them, and we will try to address them as we can within the chat.
Alrighty, so I hope my screen is visible. Right now I don't have the live stream in view.
Yep.
So great. So thanks, Josh, and well done to the previous presenter. Really enjoyed the presentation, and it's nice to see that you'll see some of those themes recurring here as well. All right, so for me, I've got about an hour of material. I'm sitting in my Madrid home office, so not as late as in Japan. It's getting to about 8 p.m. here. So this presentation will be about MATLAB, right? And often when you got a presentation about MATLAB, it's about learning a bit of MATLAB. Well, that's not really going to happen in this 1 hour. It's not enough. 1 hour is not enough to learn a new programming language. And so this hour needed to be a bit more focused. So this hour will be mostly about MATLAB and audio plugins and MATLAB and deep learning. And in doing that, obviously, there'll be a few more ingredients that will be relevant to the NAP competition. But I have a few more resources on how to get started with MATLAB more generally, but not in this 1 hour really. So let's keep in mind, these will be our two main topics, roughly half each, obviously interleaved and related. Quickly about me. I've been with MathWorks for about 15 years, and these days I work in product management. I work in a toolbox of MATLAB. It's called Audio Toolbox, but I also have an oversight of other toolboxes in general for signal processing. I have been using myself MATLAB for going almost to 25 years. It means that I started a long time ago. Those days, neural networks was a course in physics. All you studied about neural networks, very theoretical. And so that means also my core background is not in deep learning, although as a DSP person, as the bottom item here, obviously I got a bit up to speed with that. But good to know if you have questions that my main background is in audio and DSP. So I first studied physics and I have a PhD in comms engineering. All right, so since I was saying that, obviously in 1 hour we won't cover anything. First of all, where do you go if any of the information that you see during this hour sounds interesting? But we have a page on in support of the NAP competition on MathWorks.com. The little thing below is the actual link. Oh, by the way, a few minutes ago, my fast clicking finger, I got it wrong. I posted on the chat while Newton guys were finishing the presentation. Not very polite. It wasn't on purpose, but you got a link to the PDF version of the slides there, where all these hyperlinks should be clickable. So go and grab it from a few chat messages above. What do you find in this page? Two things to remember. There's one section full of links with some technical resources. There's some tutorial demos, some videos that go a bit more in detail, especially about plugins and deep learning. Then there's a button to download a MATLAB license for free if you're a student. So that caveat. You need to show that you are involved in some kind of education, and we'll give you access to a good stock fit for purpose for this competition. If you really want to start to learn about the basics of MATLAB these days, there's a lot of kind of short few-hour courses for getting started on our website. Left-hand side, we've got the basics, but there are some short getting started courses on deep learning and signal processing that might be worth a look if you are not very experienced and you wanted to get started. If you get stuck, I have to say that, yeah, MATLAB is known to have one of the best documentations for software tools. And for me, it's quite a disadvantage because these days I get nervous quite quickly when I use another software tool. But if you get started with MATLAB and you use something else, it makes it quite easy to solve your problems in the doc. There's also the community to ask questions. It's called MATLAB Answers. And if you've got a more specific question, feel free to reach out through LinkedIn or whatever other means. So getting back to our topics. The first focus will be on what MATLAB has to do these days with audio plugins specifically, because since when we launched Audio Toolbox about 6 years ago, we introduced a few tools specific for audio plugins. And so we'll be taking a look at how to write MATLAB code to do audio plugins. That will be MATLAB code first, how to translate that MATLAB code into native binary VST and AU plugin using MATLAB. And then we're also taking a look at how to then incorporate these networks into, first of all, the MATLAB plugins in a way that will be translatable, convertible into a native software. So to start, I just want to play a kind of a couple animations from a demo I put together a few years ago that has some deep learning in it. And I think it gives you a bit of the idea of where kind of the middle point of where MATLAB is used in engineering. It's possibly, a lot of companies that do a DSP for music, they use MATLAB. but across the board, there's many more people using MATLAB. And so when we put together these automations, let's call them, to turn MATLAB code into a native plugins, the idea is not to make plugins for creative operations on content. In fact, we don't do any creation of instrument plugin, which is a bit of a bummer, but hey, you can't do everything. And so we need to be selective. So our focus for the plugins was to make audio engineers, acoustics engineers, speech engineers a little bit more productive. So to give them a way to prototype whatever DSP or machine learning algorithm, not specifically to do production, to work in music or to work in DAW. Use the DAW basically as a way to see how a kind of a dry MATLAB algorithm would sound in real time. So this example is about wake-up word detection, right? So that the main application, I'm sure you know what I'm talking about. Hey Siri, is this, right? This is my shabby old office. And then if you look at this from a MATLAB perspective, some of the general idea is that when we write the code to prototype something like a wake-up word detector, we have all the logic in place to buffer an input signal as it streams through the algorithm. In general, in this case, to extract features or to do some kind of transformation very often, to feed those to a network, and then to do the inference. These three things, generally, this is, it will look like pseudocode is actually MATLAB code, will look like these kind of the core of the maths. There's some MFCC Fisher structure in this case, normalized and then passed into the classifying method of a deep network. And then there's a bit of post-processing to do some debouncing of the detection and to generate a sound. All these things go into some wrapper code that we'll take a look at in a bit of details in a few minutes. And then what you did with this wrapper code, which is MATLAB code, is that you call a command called generate audio plugin. This is the API. There's also some apps where to do this. And as you do that, that gets, first of all, translated into C++, wrapped into a Juice project behind under the hood without you knowing it, and then built with the format that you select. And as a result, you've got, in this case, your VST, this is Reaper. And so in this case, it was.
Okay, I'm testing a prototype of a wake-up word detector, trained to wake up when it hears the word yes.
All right, so that was
I'd like
played
the system to wake up whenever
in the
someone
plugin.
says yes, but obviously not when they speak any other random word that's not yes.
I'm showing this a bit to make fun of myself, right? Obviously, you're not going to make music for this, right? And it's true that you won't find in MATLAB any super duper example to make great music. You'll have to inject quite a bit of creativity and pre-existing idea, I guess, to do something useful in the next 2 weeks. We won't get there. What we do is turn some DSP and deep learning code written in MATLAB into something that can be auditioned in real time. All right, so this slide is, in a very compact way, of a way to give you, from a very high level perspective, the basics of putting together a plugin using MATLAB code. What is this about? This is a high-pass filter. There's no deep learning in here. It's like what close to the simplest thing that you could do without being too trivial. So what is this? You can see, I hope you don't have this ugly Zoom toolbar at the top. You can see that the first line, it doesn't begin, if you're familiar with MATLAB, with a simple function header. It's a class definition. We use classes to enable you to wrap up plugin code and inject the right metadata in here, because it gives a way to put the right stuff in the right places. First of all, this class inherits from an abstract class called audio plugin. And it's got some basics, rules in how to expose things. Parameters of the plugin is first declared as public properties, so they're visible from the user. You always provide a method that's called process. That method, this is just the this pointer, as you would call it in C++. So it's just got an input and an output. The number of columns in the input will say how many channels you're passing in. And then the other thing about classes they give you property of the classes as routine and data property. What do you do with properties? Well, you do useful things for real-time audio. For example, you store states for any algorithms.states, like in this case a filter, hence choosing at least a filter. In the case when we process, we pass the current state of the filter inside the filter function, and we export the filter, the updated states, and we save them again. So fairly trivial. And then also, typical useful things is that you store results of expected computations. If you want to expose the cutoff frequency of a filter, well, you don't use the cutoff frequency itself to do the actual convolution. You first need to turn that cutoff into some filter coefficients. You only want to do it when it's useful, not every time. And so then you use the property to store things. Anyway, this is fully documented, but this is the gist to get. You need to write a class in Matlab to auto plugins. Okay. When you then use something like this, you create an instance of that class. You call that an object. Okay, and that object will expose the what you created as parameters. So you then change it using, for example, the dot notation by referencing the property, and you use the process method to pass an array and take out the output. You can use either the dot notation or the function notation, where the object is the first input, the object instance, right? So when you do things this way, it means that you enable MATLAB to parse this object and to understand how to automate a few things. So the parameter, in this case, you declared it as a parameter, but you need to pass a few more information in order for MATLAB to automate drawing of an interface. What does an interface need as a bare minimum? Well, it needs kind of a name that could take it from here, but it needs to know between what range you need to change the parameters. You want a minimum, a maximum, and also possibly a variation low, because for frequency, you don't want to go linear. So there's something else that you tend to add to these objects, some metadata that's called plugin interface, where you basically give that information. Optionally, you want to give the units, you want to give a variation low, in this case, logarithmic, from a minimum of 20 to a maximum of 2000 in this case. And that's pretty much it. Okay, once you provide this, then it means that you can take the code and also automate the rendering of a user interface. And you can do that in a few tools inside MATLAB. We'll take a look, for example, this audio test bench that allows you to connect algorithms or plugins to inputs and outputs, for example, file content or input from your sound card. But also, utilities to build interfaces to this object you can use while using the object in a script, for example, and still tune the value of the parameters through an interface. So these are used inside MATLAB, but also outside MATLAB. When you take this plugin, which is called ipass.hem, and you call this generator plugin, you will generate the binary, and generate the binary with an interface. These days, that interface can also be slightly customized. The things that we're trying to help people are easy things. So there's no visualization as yet, but there's a few flavors in which you could have control over parameters, depending on whether they're continuous. They could be knobs or sliders, but they could be also switch and drop-down menus. So there's a little bit of customization by using film strips, which are long images that are collections of all the 256 aspects that a control might have. You could customize your controls however you want. Now, this is the small print that you find at the bottom of a box when you buy something. What are the things you can do and cannot do with these automations? Let's go. So, as I mentioned previously, this is centered around effects. There's no visual instruments. You can put together, you can create sources, but all the media automations with that's got to do with nodes, there's no automation for that at this stage. We are, we are keeping, improving the type of standards that we support, the types of plugin. You see in these slides, wherever you see R, a year, and an A or a B, that's the tag of our release. We do 2 releases a year. The A in the spring, it's about to come out in March, hence the coming soon. We don't really like to say when things are coming up, not to commit to anything that we're not super sure. But although 23A is coming up soon, you won't see any mention to 23A in these slides. But there you go. So we keep incrementally improving these capabilities, although the first release was delivered in 2016. So these could be VST, AU, they can be standalone. And since it doesn't say since when, but since a few years ago, we also give the possibility to generate source C++ projects. So instead of relying on all our automations, you can use your automation up to the point of generating a project. And if you are a fancier, for example, interface or something else, you can take over the generated code and moving forward with the project. All right, where to go for examples and inspiration? I want to show these two links. So there's the place at the on the left is a place of the MATLAB documentation with plenty of examples that are open code, just that you can dive in and explore. The right-hand side is the historical file sharing repositories for MATLAB community. It's been around for ages. And since launching the MATLAB plugin competition with the Audio Engineering Society, we're putting here a tag. And so by using this AES-COM tag, you get all the submissions to the past competitions. And two things to mention, to highlight, and kudos to Christian Steinmetz, who is not joining us today, but is helping the audio plugin competition. He, for me, was one of the best contributors to this. He came up with a very smart use of deep networks that don't just produce, consume and filter audio, but work on automating the production parameters for plugins. And I think those are two great examples of use of deep networks. But what I wanted to show you here was this page, because this will help us go a bit into MATLAB and take a look at this. So you can see this page. It's useful because it gives you an example of how to customize the interface using the API that we use, and with very simple effects that many people know. And so once you know the effect, you look at the code and it makes sense and it helps you learn. At the bottom of this, there's only one example on deep learning, which it's a denoiser. Don't get too excited. This is not like the denoiser that Adobe released a few months ago, or the ones that's used, I'm sure, by Zoom and Teams. This is a very crude denoiser, just a basic denoiser to get you used to the general idea. It's linked to another example that we ship. I'll just quickly show this to you. It's called Denoise Speech using deep learning networks. And this example gives you a couple of choices between kind of a convolutional network and a fully connected, and the plugin uses the fully connected. It's based out of a very crude idea that people were experimenting with a few years ago, up to 5 years ago. It's just short time Fourier transform fed into the network that sees the latest 8 frames of the short time Fourier transforms. It's given the latest, the current as target to minimize the distance between the two, and it basically spits out a magnitude estimate, and phases is reconstructed from the input. Really a crude, but the crudeness is good because you can concentrate on the flow in this case. So I'm not claiming this is actually any good, and we'll see how it sounds. Going back here, you can see that this bit of page has a click to inspect the code to actually generate the plugin right from here. And also, in this case, it gives you instruction of how to download the actual networks. Most deep networks that ship with MATLAB, and I'll give an overview in a few minutes, they don't ship with the installer, not to oblige people to install, tens and hundreds of gigabytes for folks that don't use them. So you first need to go and download those from MathWorks.com, and it says you how to deserialize and then save it locally so that the plugin sees it can use it. But if I go then in MATLAB, that's how the plugin looks. I just want to walk you quickly through the code to recognize a few patterns together. The header, there's the class name, and then also this minor audio plugin. That means inherit from abstract class audio plugin. That's how plugins are named in MATLAB. That's the plugin type in MATLAB. As we scroll down, the first thing we meet are a few public properties. Are the things that you see from the outside world. Okay, and there's some of that horrible information and code to configure the ranges of this is copy paste code. it creates a simple interface where you define whether you want a kind of a knob, where you want it in the grid that you instantiate, and what kind of variation laws you want to ask for those. This is something that I don't want to discuss now, but this is something that says how to optimize the DSP and the deep learning layers of the network that you use using the local CPU, so using optimization libraries. And then we go into a bit more interesting things. The heart of everything is the process method. I was saying this is the this pointer, this is the input audio, and this is the output audio. So what happens in between? This is where everything takes place. Every time a new frame is passed by the DAW or by Matlab, depending who runs this, then this method is called and something happens to that little buffer. The buffer is simply what the DAW gives you. It's not the buffer that the network needs to see. As the Newton guys, I love your slides, guys. I think they were really nicely made, and they explained well the concept. So what we're seeing there, it's similar to the stuff that you automate without the user needing to worry. Here, the user has to worry a bit. The point of no worries comes from reusing examples like this, but the code is here. So what happens here is that we get the audio being, for example, converted to 8 kilohertz, because that's the rate that the network in this case was trained to. And also taking, so that's the decimation. We write also to a longer buffer to make sure that the network gets called only when we got enough samples for it to be used. And then you see here that we've got a bit of a a short time Fourier transform right into the buffer. And then in this case, in this line 2024, we're calling the noise model. And then once you call the noise model, we reinvert into the time domain, and we write to the buffer, we read back from the buffer, convert from 8 kilohertz to whatever sample rate is passed by the DAW, and we're ready to create the audio. What's in the noise function? Well, you see that's the heart, this is the brain. This is where deep learning happens. This is the deep learning prediction. So this network was pre-trained, serialized into a MATLAB format, and in this case, it is a MATLAB network, and it's read from a file in an agile serialized format into this object, which is persistent. So this is just an example of pattern to have things persist over calls, and then you call the predict method on that to produce the output of the network. So that's it. From a user perspective, how do you use that? So let's call, for example, an instance of this. An audio plugin example is the package where we show all the examples in the doc. And so if we let this display what we can see, the user can see the parameters that were specified basically in that interface. And if you do dn dot threshold, you can change to this. That's obviously changed. That's how you change it programmatically. If you have, for example, this is a bit of noisy audio. We can call this that I created with a simple script previously. Okay, so audio NFS. We load this into the workspace. So this is a bit of noisy audio. If we listen to this.
The discrete Fourier transform of a real valued signal is conjugate symmetric.
All right, so this is just a dummy voice that's been around in MATLAB for ages, and then washing machine from, I think, some Mozilla data set, just to experiment with noises. And this network was only trained on removing noise machine noise, and it doesn't do it all that brilliantly. Because it's an example, but some of the things that the DAW would do is that it would, for example, set from the outside the sample rate, and so we make sure that we set the sample rate to the plugin, so the plugin is aware, and when it needs to do the decimation and the interpolation, it knows what are the input and output signals. And then we can say that our output is dn dot process of our input. And so our input was a single channel, that's the number of columns of that many samples. And so the output will be just as many samples of a single column. That's what we can expect. And that's it. Will it be very clean? We can try.
The discrete Fourier transform of a real valued signal is conjugate symmetric.
How better than the other one?
The discrete Fourier transform of a real valued signal is conjugate symmetric.
Not quite, right? No miracles, right? So old model, basic principle, no brilliant latent space. It's just a mask on the short time Fourier transform. But the idea, I think, is what counts. Other things that I wanted to show you, and I'll quickly bring up something for me on the other screen to make sure that I don't forget about two things, is this audio test bench. So if you go to MATLAB's got a number of built-in apps, and under here, signal processing, you'll find this audio test bench. You click on it, will bring this up. This is, I showed this in one of the slides before. So say that we put, we got this as denoiser, or we can also put the N here. This will bring in our object, and you see that it will render the interface based on the metadata that we put in the plugin. So we don't have to design the interface using MATLAB app designer or guide or whatever. This will do it for us based on that metadata. And so this is the place where I can directly hook this up to a file, for example, or an audio source, or kind of the device reader from any sound card. I can put this in the loop or bypass, in this case, right to the output. So you should hear it. And as I then run this, jumping around, isn't it? It's just about, in this case, if you run it without compilation, to do the right job without kind of a live YouTube live stream or a Zoom connectivity. But the other things that I could do here is also to load the binary version of the plugin. Okay, so for example, if I did like that and load the compile plugin, and so this could be a plugin that I generated with MATLAB or any other plugin, because MATLAB can also host binary, VST, or other plugins. Then it will take focus away from me in this case, and then give it back. So that will you can see that when we import another plugin, we don't honor the plugin UI. We just paint a basic UI based on the definitions of the parameters, and this might well be
the discrete Fourier transform of a real valued signal
faster.
is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric. The discrete Fourier transform.
Really not the end of the world, but at least you can hear the difference. You can at least it's confirming that it's doing something. Okay, and all right, so I'll go over things like media connectivity later on using slides. What I want to point out here is that this is a nice place to show you the idea of doing real-time audio in MATLAB in general. If you click that generate MATLAB code from the app, it shows you the basic principles of running live MATLAB algorithm on live audio. And it's not that difficult. The basic idea is a loop. It can be a while or a full loop. I remember back in 2000 when I started using MATLAB that I had this idea of writing a simple loop and doing audio processing real time. Obviously, it didn't work those times. But the idea here is that you're using objects to read from files or a sound interface. So all the initialization and memory allocation to deal with the communication with the driver is done outside of the loop. And then what we're doing inside the loop is just shifting the pointer to the audio buffer. And so in MATLAB, it's quite easy these days to do real-time audio, just writing code. You don't need to go to the app, but the app can make life easier for some people. In this case, this system under test was the hosted plugin, which was the VST2 in this case plugin, that was rendered as a MATLAB object. So if we run this in isolation like this, you can see that SUT will be it will be called a VST plugin denoiser with the variables that it exposes. And so this gives you a way to test plugins in a non-interactive way, in a programmatic way. If you need, for example, to verify that the plugin outputs the right output for a given test signal, you can use MATLAB for that. Why do I say you these things? Because I don't believe that you must use always one tool, just MATLAB to do all the job. MATLAB may have a few things that might help you in the process while using other tools too. All right, let me, I haven't showed something around the network that's in here. So let me quickly say about things. You remember that the network was saved into this file, or that was what the example was recommending. So if I take this and take a look at it at the command line and see what this is, it tells me this is a serious network with a few layers. So if I type the name again and ask for the layers, it will show me what the layers are. And so it's got an image input. Well, it was working on that short time Fourier transform. So that's the way we call it. It's a 2D input layer. And then it had a number of fully connected layer following, right? And so if you then go here and you feel that you want to investigate, for example, what's in layer number 8, that you've got the details for every layer. So you got the typical MATLAB ability to interact with this. Another thing that you can do, well, another approach, let's say, to look at networks and to deal with networks is through apps. This app called Deep Network Designer. In this case, we're looking at this and at this network that you got here saved in our workspace. Denoise for the collected network, that's the one, and we import it. It will give us kind of a visual representation of the network, and this app gives us a way to, oh, sorry, it's still, it had the, this is a visual representation of the network. From here, I can select, move around, delete, drag other layers from here, and for every layer, then possibly customize all the parameters in here. There are some, let's call it DDSP layers in here, like the STFC to use. Go look at the example of, I can't cover everything. I'm fearful that I'm going into too much detail here. Let me jump out of MATLAB and go back to the slides to make sure that you have all the key bits of information here. We went through this example and we talked about loading plugins in MATLAB, or hosting, as we might say. All right. Now, something that I hadn't showed through the app is how to do another kind of automation. When we've got the plugins with their parameters, we can change them numerically through the API programmatically. We can change them through those apps that I showed by turning with the mouse pointer, or we can link those parameters to MIDI controls. So if I run this command, configure MIDI on the denoiser, you remember maybe, hopefully, that it had these 5 parameters. And so what do you do is that it gives you this this UI. You click on one parameter, you go to your the surface, controlled surface, you touch your control, MATLAB senses what you touched, and immediately locks the plugin parameter to the controlled. And so even if you're using the plugin in code, by moving the MIDI controls online, offline, while you execute the code, while you don't execute the code, the audio plugin in MATLAB will reflect the position of the control. All right. Useful for a few workflows. All right. I can't believe you. I'm already halfway. Well, I better be. So that's what I was planning to cover just on audio plugins, but I've started to tell you a bit about deep networks, haven't I? Now is the time to go a bit deeper into discussing deep networks in MATLAB and see a few things about how the whole thing works. And the things that I really would like to cover is the various approaches to how to get hold of a network or design it. The possibility that you have in terms of using MATLAB with PyTorch and TensorFlow, where, as we know, most of models live and are developed. And how do you go then to implementations? Why do I care about this? Not because I want you to take the network and deploy to chips, even though this is what MATLAB users do. But as I said, if we want to plug in, the trick is to take the MATLAB code and convert it into C++ before it gets wrapped with juice wrapper. So we need to make sure that when we use a deep network in a MATLAB plugin, that network, as we say, supports the ability to be converted into C++. Ideally, everything does. In practice, not quite everything does. So it's just important to know the fine print. All right. So in general, when we talk about deep networks, I think probably at this point here, we don't need to say there's a network in the middle, and then there's an input and an output, but those input and output can be different things, right? If, in the case that we got a signals and we got a choice, it can be a classifier. Why not developing a plugin that's a classifier? That's also a possibility as a way to prototype an algorithm. It could be a signal processing engine to process the input signals. It can be something that derives some parameters, like some of the work that Kristen had done in that example, for example, by analyzing some signal, understanding which, for example, effect parameters you want to apply for automated mixing, stuff like that, for example. Or in other applications, it's just about extracting deep features that describe the signal. Whatever. All of these things can be done, obviously. And in MATLAB, I would highlight 3 possible strategies to build a model. Either you can define it from scratch using the app that we've seen and using the equivalent API that we took a glimpse of. MATLAB ships with pre-trained models already in MATLAB that you can, so the ones that we saw together, yes, it was pre-trained, it was pre-elementary and basic, but we ship some state-of-the-art models that could be reused. And those are useful because by doing transfer learning, suddenly you don't have to, if your application is reasonably matched, then you don't have to do the full training, you only have to train a few layers. And the other idea is to import it from another environment. So from TensorFlow and PyTorch, either directly or through Onyx, for example. Those things are various things that are supported. So let's go quickly through those options. We thought about these 2 conceptually different ways of composing the network. If you're kind of a command line person, there's the full API to build just networks as a topological connections of layers, or you can go drag and drop in the app or mix and match. All right. There's also the ability to, there's another API in MATLAB to write deep networks by going more into let's say the mass of the layer, by defining the layer by the way of how they works, using some API that makes them auto-differentiable. That's all documented, and I don't want to go too much in detail there, but feel free to go there if you want to learn more about those. And then, as I was saying, these days, MATLAB comes with a number of pre-trained networks. We've got for a couple of years, this new GitHub repository that attempts to summarize all these models that are scattered in multiple places, but they're state-of-the-art models. And there's quite a few for audio, speech, and acoustics. So I want to give you an example of what it means when we ship pre-trained models in MATLAB, and I'll use one of these state-of-the-art models. It was developed by Google. It's called YumNet, and what it does is sound type classifications. It's trained on over 500 different sound types, and it's able to classify and segment different contexts of recording. And it's one of the models that we ship, and it's easy to understand. Right, so that's basically what it does. You give it a waveform, it processes it and gives you a choice between over 500 categories. And so it actually, the model doesn't consume the raw audio, the waveform, but it's been trained using a specific strategy for feature instruction times frequency transformation. If I don't remember that, these are MEL spectrogram, whatever. So what do we do when we ship these networks that are state of the art and pre-trained? We do several things. First of all, we give you the network in the same form that you've seen the denoiser earlier on. So the bare network that can be fed, featured, can be trained, and can be inspected. We have in this case the MEL spectrogram in general, but when you need to extract the right MEL spectrogram that was used to train YAMNet, you need to know what kind of window length they use, what kind of band spacing they will use. It's hell to know about all those parameters, and more often than not, you don't get it right. So what we try to do is to package the MEL spectrum we have with the right parameter choices, so you got exactly the same parameter choices to train the network, and you've got also the conversion from whatever sample rate of the signal to the sample rate that the network uses. It's not the first time that you hear about those things, right? Today, it's a common pattern. Try to make it easier for people to reuse state-of-the-art networks, as the Neutone folks outlined. Why do I say that? Because we also have a kind of new objects that do bag of features for audio extraction, but they can be difficult to use. And then we also provide some helper functions to make something useful of the output. Look at this tree of classes of these ontologies. It's a bit of nightmare. So perhaps you don't care if it's a horn of a lorry. You care just if this is a horn. So you want to be able to look at the right level of hierarchy. But to make it short, we provide helper functions at the input of the network and the output, and then we provide an abstraction for casual users. If you really only want to label sounds to train some other system, you only need to segment. You can use a high-level function called classify sound. You pass it a waveform at the sample rate, and it will give you the regions of interest of some sounds that it found, for example, right? But for this kind of exercise, to build plugin, really, you want to look at this level of abstraction, okay? But so this is a list of the few state-of-the-art models that we supply with the full support of all that kind of abstraction. So layer, kind of casual layer to just do the job, network plus, pre-processing and post-processing helpers. So you can see CREP, for example, for musical pitch estimation here. OpenL3 and Vigish, these are for embedding extraction. If you want to do some more understanding of the feature and you want to work on advanced feature, these are good choices. We talked about YAMNet vector. iVectors are very useful for speech processing, but actually they're not deep learning. These are systems or traditional deep learning models, and these are the applications here. But there's also that beyond this, there's a full list of other models where, yeah, some of them state of the art, like X vectors, for example. ComtestNet is used very much for speech separations, and so not for all these. We've got examples. Some of those are on GitHub. We don't provide the full spectrum, but you still may find useful stuff to reuse in all these resources. And for example, see this. I don't have it here, or do I have it here? The network that I showed you earlier, denoising, this one. Okay, Mozilla Common Voice Dataset, the basic CNN receive. Oh, I was wrong here. The one that I showed you was fully connected. It's a recipe. It's pretty old, but yeah, there are other like these. There's a dereverberation one, etc. Now, that's about all MATLAB. Having this allows you to stay in MATLAB. I had a video where I showed what it takes, for example, to transfer learn some of these networks. Let's take a look at that. I think we probably have just about the time to take a look. Let me make sure that I moved out of my presentation, and let me unhide this slide and present it. This is what it takes, for example, to take a pre-trained network and transfer learning. So in this case, we're taking YAMNet to identify some noise of an air compressor, to identify the damage of the air compressor from the noise. So we've got the data sets provided by somebody, and we want to retrain YAMNet on that new data set to have YAMNet understand what kind of damage an air compressor have based on this noise. And so this is YAMNet. It looked inside the Deep Network Designer. We strip away the last classification learner. We only care about classifying between 8 different types of condition of the machinery. We connect. We import the data in the right format, which was that MEL spectrogram. In this case, you see it monochromatic representation of the melt spectrograms, and then train the network with the new data. But because all of the network converged, we're really only training the last layers. And so if you look at the time elapsed here, these are only really few minutes on a CPU in this case, on a single CPU. So that maybe a nice follow-up to the question and the answer on the impact. Sometimes, especially in industry for industrial applications, much of the suggestion is to reuse, to go on the shoulder of a giant and try to use state-of-the-art models on your own data. And you see, in this case, that's what that example does. All right. What about you don't have the model in MATLAB? There's many ways to take from other environments. I won't maintain that this is straightforward completely and that it always works. Going from one environment to the other is often painful. So it may be that you'll have to go over some little issues, because sometimes, for example, the translator cannot translate one layer from one environment to the other, and it will replace it with an empty layer. Well, you need to go in sometimes and recode or replace the empty layer with the actual corresponding representation. That said, there's the way to do it with Onyx. You can go in and out on TensorFlow, and you can go in from PyTorch into MATLAB these days. Links here to these resources, these pages of documentation. You can see there's plenty of different types of functions to import networks from different environments, sometimes in slightly different ways. So go and focus on whatever is relevant if you need to use a network that was developed by a colleague or is available out there developing another environment. More general, MATLAB is not just about TensorFlow and PyTorch or Onyx. MATLAB can also talk to Python. Why would you want to do that? Many different reasons, but and I'll go through a few, but this, for example, you can use MATLAB as a master and call out to Python. In this case, in this loop, using the forward prediction of a network available in Python. This is the way to call a Python object or a package in this case, or I don't remember what this was exactly, but you basically, these were written in Python, and the code here is all MATLAB, pretty straightforward. And easier and easier with the years. Same thing is roughly valid from Python as a master as well. The thing to be aware is this MATLAB engine is just basically a programmatic API from MATLAB, and you call with the dot notation things that are on the MATLAB path. So this is, in this case, is MATLAB function. So why do you want to do that? Well, for example, this is a possible use case. This is where you've got a framework, Python and TensorFlow, where you've got all the network set up in the training loop, but you want to use MATLAB to label and pre-process or augment your data set because DSP may be simpler there. Well, you just link in the tool, you call out to MATLAB from the Python training loop, and that's also possible, right? There's plenty of resources. I put down two possible links. This is about training in Python with MATLAB in the loop. It's a GitHub submission. And this is a page on MathWorks.com with various resources and using MATLAB and Python together. Just to strengthen the importance of using MATLAB, thinking out of the box, not just about training and deep learning models, but also all that comes with it. If you work in deep learning, many times 80% of your work is on the data. So there's a lot of work to do around deep learning that's not just about the network. It's about, and sometimes reusing a data set for a different purpose. Well, you want to have the right tools to the right resampling, the right segmentation, the right signal processing, all that you need. And aside from things specific to labeling and segmentation, MATLAB's got a lot of new things for feature extraction, a lot of new things, for example, for randomized, automated augmentation of audio. See, this is a new object called audio data augmenters that allows you to have either serial or parallel pipeline of augmentation effects that you can control randomly to try and improve the accuracy of your model if you don't have too much data available. Right, so I'm getting into rambling and listing of window shopping capabilities to try and list as many pointers that might be useful. And so without even realizing, I'm getting towards the end of the second part of the presentation, which is good because we're close to the end of the time that I had allocated, although I know I started a little late. So the other thing to know is, once you know about all these things related to deep learning, what do you need to know to make sure that if you use a deep network in MATLAB, it can be used in the plugin. These are the main ideas. So as we saw with the plugin, it's not just about the network, but it's about the network and all the MATLAB code that relies around it, the signal processing, the buffering. And so that what we do is to generate C++ from the whole lot. And inside it, there's also the network. So as far as the network, in general, MATLAB can be translated to embedded code for different types of devices. It can generate CUDA, it can generate C and C++ run CPU with or without optimization libraries, and it can generate also HDL, Verilog, or VHDL. What we really care about here is mainly the CPU root. Well, why didn't I include GPU? MATLAB can generate CUDA. For plugins specifically, we haven't made things any easier, so I won't mention about that. Don't think about generating CUDA from MATLAB while using plugins. If you're not doing audio plugins, that's also possible. But if you are doing plugins, it's beyond recommended. The automations work for C and C++, C++ for plugins, right? And the two things to mention are these. You can choose for your network to go either library free, so basically vanilla C++ for the network layers, or you can choose to use a finite set of optimization libraries. Well, you might think, oh, why are you not using that optimization libraries? I wish. We're not using everything. For plugins, we're allowing ARM optimization for Cortex-A to try to go through Juice project generation into Linux plugins and perhaps being able to run on Cortex-A based things like Raspberry Pi. Although it's not a workflow that's massively used, but it's possible. But the main thing for optimization to look at is Intel. Okay, so think about mainly library free or Intel as the two main options. So here they are: vanilla C++, or as it was once called MKL-DNN. I think these days it's called OpenDNL, and that works on Windows and Mac. Obviously not M1 Mac, but Intel Mac. And this is a bit, if you've got good memory, I said while opening up that plugin code, I said I won't talk about this, but this is important for code generation. So if I go back to my to my MATLAB and my denoiser plugin that I was showing, I had here at the top where I had the metadata. I had something else under here, which was called audio plugin configuration, right? And here I was specifying two parameters: deep learning configuration and code replacement library. Forget about code replacement. This is about the replacement of the DSP. So optimizations, SIMD optimization for things like filters, FIR filters, and stuff like that. But the thing to pay attention for deep learning is this. You got two options here, either MKL-DNN or none. If you put none, then the plugin will generate vanilla C++ when building the library. If you select MKL-DNL, then the plugin will link to the Intel libraries. If you do this, you need first to install the libraries, compile them, making sure they're on the path, you configure your OS, etc. Everything's documented, but it won't just happen the first time that you do it. All right, if you in terms of support, if you're using a network that's fancy, you don't know whether it will generate code, there's this command that you run on your network in MATLAB, and it will tell you if it supports code generation and which of the optimizations it will support or not. Right? In an ideal world, everything will support every output. In practice, that's not the case. All right. And so I hope with that I'm pretty much honoring what I had set out to talk about. I cover mostly the infrastructure for automating the generation and the hosting plugins, and in general, deep learning, as well as how to use deep learning in plugins. And I hope I touched a few other things that can be relevant for the competition. Josh, you haven't interrupted me. I don't know whether it's too late and people have started to fade away. Or
No, we're still here. We're still here and we're going strong. Thank you very much, Gabriel,
good stuff.
for that amazing presentation. Doesn't appear that we have any questions in the live chat. I know that may have been quite a bit of information for people to digest, and that's okay, because we have this video online and you can watch it back. You can slow it down and pause and rewind and loop as much as you'd like. So for people that are using MATLAB, I hope that you've enjoyed that presentation. Once again, there are trial licenses that are available on the MathWorks page that I have linked in the chat for you if you would like to use MATLAB to build your neural audio plugin for the competition. And before we sign off, just wanted to say thanks to you, Gabriele, and thanks to the team from Qosmo, Andrew, Christopher, and Naotake. And thank you very much. I really appreciate your efforts, and I think that a lot of people really got a lot from this. So thank you very much.
Thank you very much for hosting us.
Yeah, thanks for having us, Josh. Also, just to maybe finish off, give a sort of projection for the next week, the next live stream. So that'll be our third live stream next week, and for next week we actually have Jatan Chowdhury, who will be on giving more of an overview of RT Neuro, and getting you up to scratch with RT Neuro and giving you a sort of tour of the code base there. We also have Philip Esling from Urcam, who's going to be doing a talk about efficiency around like building neural networks and models and neural audio. Like how can we create more efficient networks and reduce training data to build models, and kind of the whole sort of topic around the general theme of efficiency with neural networks. So lots more exciting stuff to come, and yes, please tune in next week for more neural audio themed talks and presentations.
Yeah. And for anybody that's interested in getting involved in the competition, be sure to check out the information on theaudioprogrammer.com/neural-audio. The link is in the video description below. And in there, there's also a link for you to join the Discord if you'd like to team up with other people to create your own neural audio plugins. So maybe you know a little bit about MATLAB and you're looking for somebody that has some experience with neural networks, and you want to team up with them and create a neural audio squad to chase after some of these prizes. Yeah, hope to see some more of you in the Discord. The chat in there has been a little bit lively as well. So, and with that, I won't hold our speakers up any longer. Thank you very much. Once again, thank you to everybody who tuned in and who is tuning in afterwards. And we will see you next week.
Thank you.
All right.